right, we're kind of what I'm doing is I'm using polymer classes as kind of a segue into rheology. We talked about rubber bands, and we'll talk a little bit more about a rubber band at the beginning of this class. But I'm kind of arranging it in a way that I hope kind of complements the subject matter of rheology. We won't spend a whole heck of a lot of time on rheology. You have posted videos, a DMA video, which I posted kind of with the last lecture, and with this lecture, and they kind of go hand in hand anyway. I have another lecture showing the operation of a melt flow indexer, and I picked that particular video because it's the melt flow indexer that I have in my lab. It's the same model. And so I'm kind of using a description of polymer classes to talk about polymer rheology, and what I'm playing with right now is silly putty, and that's kind of it's kind of fitting, and we'll see why in a little bit. Kind of showing we go from stress strain behavior, and we'll talk a bit more about mechanical properties of polymers later on in the semester. But here we're 100% ABS, if you remember, and this is kind of highlighting the previous lecture to kind of tie it into today's lecture. And then we went to mostly rubber, so this MAG SEBS, is SEBS with a maleic anhydride graft, excuse me, so we're 90% thermoplastic rubber. And you see a big difference in the percent elongation that the material can undergo during the stress strain test versus where we started. And so big difference. And this actually, it's a record, and I don't think anyone's beat it yet. The only people that had come close was the commercially available Ninja Flex, and this is kind of a record for a 3D printed material. So it's I'm champion of something, at least. Theory of rubber elasticity again, and kind of showing this where we left off last time of this Jablonski diagram. You know, we make a big deal for most materials about bond energy, bond strength, but that's not the case with rubber materials or elastomeric materials. And the chains elongating, all those chains are going to be held together by the same carbon-carbon bond that's in a regular plastic. It's just those chains elongating kind of facilitate the stretching of the rubber band, basically. And they have light cross links as compared to a thermoset, and so a little bit different behavior. Again, theory of rubber elasticity, it's an entropy driven process. This has some, well, it doesn't really snap back. This would be more viscoelastic, and we'll talk about viscoelasticity a little bit later. I'm looking around, if you're wondering what I'm looking around for. I was looking for this, my rubber band. And hopefully you've had a chance to try the little lip trick where you stretch it and it's hot and you let it kind of snap back and it's cold. It's an entropy driven process. It's pretty cool. Kind of the same thing, entropy driven process, what I just showed with the rubber band. I didn't talk about this. I should have talked about this, the stretch ratio, and it's kind of interesting. And this is one of my children, but a long time ago, actually stretching a rubber band. It's kind of cool doing this stuff at home, and because my children get interested in it, and so it's really kind of neat. So I have a junior TA that you've seen before, Isabella, who helped me make slime. And anyway, so stretch ratio alpha, it's sometimes called the extension ratio. And I should have labeled this. I apologize for not labeling this slide. I should go back and edit it. But alpha is the stretch ratio. I don't know if I need to, because LF is the final length over L naught, which is, of course, the initial length. That equals to 1 plus delta L over L, and 1 plus epsilon. So delta L over L is strain, and so 1 plus epsilon is the stress ratio, and stretch ratio. Just to kind of point this out to you, in other books, sometimes it's called lambda. We tend to run out of Greek letters in engineering, so alpha can refer to a lot of other things as well. I thinking X radiation right now because of another class I'm teaching at the same time. But lambda also could be wavelength because of the same class. But anywho, stretch ratio, that's something that we kind of apply to rubbers. The reason why I bring this in is there's no linear elastic response for a rubber. And so if you look at a stress strain curve, you know, you always have the linear elastic region. And so let me try to draw it here. And typically we have a stress strain curve, and I'm really sorry about my axis. I'm drawing it with a mouse and not my pen today. So you have a stress strain curve, and you typically have this linear elastic region, and then, you know, something like that. Okay, and we don't really have that with rubber materials. And I've lost my pointer. I'm sorry. We don't really have that with rubber materials, but this would be the linear elastic region here, and then here would be kind of the yield point, and here would be UTS, kind of basic stuff. But we really don't have a linear elastic response. And so if this is plotted against lambda, I grew up, actually kind of not grew up, but I learned it as alpha, so I kind of stick to my old notation. If you look at it, you know, we kind of have this real response, and this is pretty much a stress strain curve. If you realize that alpha is 1 plus epsilon, or lambda is 1 plus epsilon, this is really a stress strain curve, and so there's not a real linear elastic response. Temperature, there's a temperature response as well, and we've kind of seen that with our mouth and stuff like that. But it's also proportional to this stretch ratio, and so it's actually kind of cool. I may come back and revisit this when we talk about mechanical properties. The key point I want you to take away right now is that there's no linear elastic response for a rubber or for an elastomer. Temperature response of polymers, and so now we're really kind of getting into rheology. I started talking about rubbers because, or elastomers, because there's this rubbery behavior when you heat up thermoplastics. And I'm using, again, the classifications of polymers as kind of a segue into rheology, and hopefully it helps kind of put everything together in a big picture. That's kind of the goal of me kind of presenting the material in this way, rather than, you know, saying classes of polymers, let's talk about rheology. I'm trying to kind of mix it up a little bit, so it's easier to connect the dots, kind of thing. That's my goal anyway, and hopefully I'm successful. Hopefully you're learning something from this and enjoying it. So again, I will show this this slide a lot, how we classify this stuff. You know, so we have thermosets, elastomers, crystalline and amorphous, and I always throw in semi-crystalline. The classifications, you can kind of continually subdivide them. Most people say thermoplastic, thermoset when you ask them classes of polymers if they're into that kind of thing. Thermoplastics, thermosets, so, and elastomers. So sorry, I'm using the same animated slide. Didn't realize it this time. My apologies. Amorphous is what we're going to kind of get to talking about now. Heavily crystalline polymers. Well, let me just go to the next slide. Polymers rarely melt. Okay, is the point I'm trying to get to. But all polymers have a glass transition temperature. Amorphous polymers don't have a melting temperature at all. They just kind of get to this kind of blobby, blobbly, blob, 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 blob state. Crystalline polymers, on the other hand, can kind of be said to melt, and to some degree semi-crystalline polymers. But there's kind of this grayness in polymer science and polymer engineering anyway. So you kind of have to accept that from time to time. There's no absolutes, and I keep playing with my silly putty. It's very fun, actually. So polymers rarely melt. All polymers have a glass transition, and we denote that with T sub G. Amorphous polymers do not have a melting temperature. At elevated temperature, the material is liquid-like but very viscous. And viscous is kind of getting into polymer rheology. And so that's kind of something that we want to kind of start paying attention to, is these terminologies. Below the TG, there's little to no thermal vibrations within the polymer chains. And so if you're familiar with the concept of phonons, and I've talked about it in other classes, phonons is how heat can get from one side of something to the other, basically a phonon. And it's also, a critical component in indirect band gap semiconductors, so LEDs. Phonons kind of play a role. It's a thermal vibration. And so we're seeing something like analogous to a phonon when we start heating material above the glass transition temperature. Okay, so we heat the material above the glass transition temperature, little to no thermal vibrations below it. Okay, when you get above it, these polymer chains start vibrating. And so below the TG, and I apologize for my painstakingly drawn picture. This is supposed to be like a droplet of polymer on a block, and I'm sorry, I probably should provide you with more high quality graphs, but I'm apologizing profusely. But let me just get on with explaining what I'm trying to actually get with my poorly drawn picture. So these are the polymer chains. This is below the TG. They're immobile. They don't move much. And you remember a polymer chain, when it moves, it not only moves laterally, but it also rotates. Okay, so there's a lot of motion involved there, right? And motion, to put something in motion takes some energy. Thermal energy is a good way to put motion, or thermal energy is a good energy to put into a system. And we see it when we melt metal. We see it when we heat treat metal. And what happens when you put thermal energy to a material? Well, you put energy into a system, there's going to be some sort of response, whether it's annealing, okay, and you can anneal polymers, and we'll talk about that, or whether it's a straight up melting like we see in metal. Anyway, so let's kind of focus on polymers. So below the TG, the chains are pretty much immobile. They're not moving much. Above the TG, there's thermal vibrations now, right? So think about it. Visualize it if you can. You have all these polymer chains hanging out. They want to move, but they can't just scoot. They have to rotate as well. And they slide over one another, right? So there's some double motion that has to happen, right? It's like a game of Twister, right? One person, it's hard for one person to move. Two people have to move at the same time. Don't know if that's the best analogy, but it's all I can think of right now. So you put some heat into the system, and you start getting above the glass transition temperature now, and that's a critical temperature for a polymeric material. And above the TG, these chains can now actually move over one another. These individual chains individually have energy now, and they have the power to roll over its neighbor, if you will. And so they can start moving around and get, yeah, let's do this, man. Let's move around. They're liquid-like. So we have different regions. Liquid-like way above the TG, so these chains are going crazy. They're vibrating. This is why I started talking about rubbery materials or elastomeric materials, because just above the TG, they're rubber-like. So you can take a rigid polymer, okay, like ABS, polystyrene, or something like that, even PVC, even I wouldn't want to heat it up, and it starts behaving like a rubber. Okay, this is an amorphous thermoplastic, okay? At low temperature, they're brittle-like properties, and so, we can break a tensile specimen very easily at low temperature. Okay, so there's brittle-like properties. These chains don't really have the energy to move around, so when you start applying a stress to them, they're just going to break. But if you put energy into it, so let's kind of think about a tensile test now. Okay, let's think about a tensile test. Our chains are hanging out with each other. They could even be entangled. They don't have any energy to move around. You put some external strain on it, it's just going to break. Now you've put energy into the system, okay, in the form of heat. These chains can actually move around. So when you apply an internal, I should say stress, but when you apply an internal stress, these chains can actually move around and facilitate elongation of that polymer, okay? And then higher, it'd be hard to get this into a grip, but high above the glass transition temperature, these chains are vibrating like crazy, so it's actually kind of liquid-like, okay? And you actually pour. Sometimes you can kind of almost. I say it all the time, and everyone else does too. Okay, melt down the polymer. Well, it's not really melted. It's just the chains are vibrating like crazy, and they can move really, really easily. Okay, and so you can actually cast it, and you can injection mold it, and do stuff like that. This is, I drew this painstakingly, but here at the glass transition temperature, so it's the glassy region where it'll behave kind of brittle. You get above the glass transition temperature, and I'm telling you, there's not a real modulus, even though I'm depicting a modulus here. You get the so-called rubbery plateau, and then you start getting rubbery flow, then you start getting liquid-like flow. And I was saying back here, this is for amorphous materials. I've actually kind of drawn the graph for something crystalline. And so if you remember, I'm going to go through this again. Here's kind of the more accepted graphic. Okay, so that kind of staircase structure that we see here is really for crystalline polymers. So crystalline polymers will kind of do similar things, okay? But when you get to the sorry, I was making sure I'm not lying. When you get to what would be the melting temperature on a crystalline, you just kind of continue the liquidy flow. And so I may have been kind of an error kind of putting this little step, because if you look at most polymer, I was talking about amorphous back here, and this is meant to be talking about amorphous. And I should have just erased it instead of showing you. I quasi made a mistake, because the more accepted depiction between something like, in this case, they'd even put properties, so they didn't want to, and I got it from this webpage. They didn't even want to put modulus, I suppose. But it's still, you have a similar behavior at the glass transition temperature. Stuff starts getting soft. These are still thermoplastics. Okay, so they will soften upon heating, unlike a thermoset, and we'll talk about thermosets in a little bit. But then you get to the melt state, but really this is only truly kind of, and it's still, I even hesitate to say that crystalline materials, that crystalline polymers melt, but they kind of melt. Okay, you have kind of a continue of the same kind of rubbery or viscoelastic state after you've hit the glass transition temperature. It just gets worse. Basically, and so the material's ability to withstand external forces drops significantly with an increase in temperature. All right, when you look at, and this is it's not a proper FDM, when it's not a Stratasys machine, it's you tend to call it FFF, fused filament fabrication. But here's my trusty Lulzbot Mini I have in my garage, and print things with it. You don't actually melt the material. You take advantage of the fact that it's going to soft, and you can actually have a flowable material. And you have it flowable so much you can squeeze it through a small orifice, a fraction of a millimeter, and make 3D printed parts. And here's an example of a mold I'm actually making for casting, and a kind of cheap advertisement for my casting videos that I'm putting out. Anyway, that's kind of the reason why FDM works. You have these thermoplastic materials, generally amorphous polymers. They do a lot better at printing than crystalline polymers. You heat them up and they go through this kind of rubbery viscoelasticy state, so they'll actually flow like a liquid. You're not melting it because the material really doesn't melt, and you deposit it again layer by layer like all additive manufacturing processes. How do we determine the glass transition temperature? Okay, so that's an important thing. We're saying that all these wonderful things happen that allow us to process a polymer. We can do injection molding, we can do 3D printing with it. You know, we have my kind of this thing, we even have my, you know, kind of explanation of materials here, right? So just above the TG, there, it acts rubbery. Way above it, it's liquidy, right? So it's technical terms on my part. So how do we determine the glass transition temperature? Well, you've seen the video, okay? Dynamic Mechanical Analyzer, DMA, and also Dynamic Mechanical Analysis, DMA. Start thinking about some terms here. So tan delta, and this is also used in dielectric materials, okay? We're using it a little bit differently, but it's still kind of the same thing because it's still a frequency response. And so that's why we see similar terminologies to what we see for characterizing dielectric materials. And anyway, let me kind of carry on before I digress too much into some story. So tan delta is the ratio of viscous to elastic response. The storage modulus is the stored energy, so that's the elastic response. Okay, the loss modulus interesting, I think that's a typo, I apologize. The loss modulus is the energy dissipated as heat, and that's the viscous response, okay? And so energy dissipated is heat. And later on, I'll show you an example of different dampening materials. But if we see the ratio of viscous to elastic response, okay, so if tan delta is high, that means the energy is dissipated as heat. That makes a good dampener, okay? It makes a good like a shock absorbing pad. If tan delta is low, that means it makes a good spring. And for dielectric materials, you typically want a low tan delta because you don't want the material to absorb your frequency if you're making like an antenna or something like that. If I'm making a dampener, and dampeners have so many applications, think football helmets, think even the pads the football players wear, a shin guard on a soccer player, safety boots. And if you've ever, I used to work in a steel mill. We used to have these safety boots, and they had what was called a metatarsal guard. So if you drop something on the inside of your foot, the top inside of your foot, you don't hurt yourself. Those are applications where you want materials with a high tan delta. Okay, and I'll show you an example of a good dampener later on in this semester. I have a little kit, and I'll show it to you. But anyway, tan delta high. If the tan delta is high, that means your loss modulus is also high, and most of the energy is dissipated as heat. It's a good dampener. If your tan delta is low, it's a storage modulus. That means it's a good spring. You know, you can make a good spring out of that. It's elastic response. How we determine, and this is probably a kind of a bad example. I have better examples than this that I'll show you later. This was actually run for me by a colleague in Cleveland, Ohio, I believe, or Columbus, Ohio. And so what we have here is we have our storage modulus, and if we go back and realize our storage modulus is the stored energy of the elastic response. Loss modulus is this blue line, and then tan delta is this brown line, okay? And generally, there's different ways to determine glass transition temperature off of DMA. Some people, and some of it's what people tend to do, okay? So some people say the max tan delta temperature is the glass transition temperature. Other people say it's this tangent on this loss modulus curve. And let me try to draw the tangent. And I have another slide, so if I don't draw it well, we'll see it again. But if you draw the tangent off of this one and the tangent off of this curve, so the linear portion of this curve, right here, this little X marks the spot is your glass transition temperature. What I tend to do is I call this the beginning of the glass transition temperature behavior, and this is the end. Okay, so after this, it's gone for the mechanical properties basically after this max tan delta, and so I kind of call this the glass transition temperature window. That's kind of my thing. I don't know if anyone else actually does. but I call this area here the TG window. There's an ASTM standard, and this is for ABS, that flat out says you take your, here we go, I'm so sorry, lost my laser pointer, where you take your TG off of the storage modulus. So that's the beginning of the glass transition temperature, the beginning of the kind of the flowy material response, if you will. Another way, so again, answering this question, how do we determine glass transition temperature? Well, you can get it from the storage modulus curve and also the max 10 delta curve from a DMA, a dynamic mechanical analyzer. Another way is dynamic differential scanning calorimetry. Sorry, and I'm real sorry I drew this by hand. So the exotherm peak would be your TG. If you have something that you believe is melting, the second one's going to be your melting temperature, and maybe you see this on a crystalline polymer. This is I have the machines I like, so I have a DSC and a DMA. I like DMA just fine, actually, and I'll show you later how I use a DMA to kind of make recipes for thermal processing of things, and we'll talk about that later in the semester. But anyway, DSC, differential scanning calorimeter, people like it. There's a problem though sometimes with polymers in that seeing the TG exotherm isn't always that easy. It doesn't always show up, and I've worked with other colleagues and I've given them materials and they can't find a TG exotherm for me, and I'll even give them a window where to look, and based on DMA data, and they still can't find it. So I've been told, you know, DSC is the way to go, but I really like DMA for the data I need anyway. Someone else may be different. All right, I'm showing the slide again, and again, just reminding you, we're talking about something else now, okay? And I thought I actually practiced this, I really do, and this caught me by surprise because I've seen it for the third time today. But the reason why I threw it in here is to tell me, the director of the PowerPoint presentation, that we're talking about thermosets now. I apologize. So thermosets do not achieve a liquid-like state, and we talked about this earlier, where we said, hey man, you know, we talk about thermosets and thermoplastics, and thermosets don't soften upon heating. I take, and now I got to go back and try it before I bash the crash course chemistry guy, because he was talking about PEX. PEX is something I've personally used in plumbing, and PEX is cross-linked high-density polyethylene, and you can use it in plumbing. And what's nice is that it's rigid, but what is also nice is that it's not as rigid as PVC, and so you can curl it. And I swear to you, I've put a metal fitting on and I heat it, and it acted almost like a heat shrink. But I may be wrong. I'm recording this, so I better reserve the right to be wrong. And so I'm going to have to go buy some PEX at Home Depot and do the experiment myself, because they say the heavy cross-linking of PEX renders it a thermoset, and I'm not entirely sure. I think maybe it has a similar number of cross-links to thermosets, but it actually, I challenge that it cannot soften. But let me try it myself, and we'll come back and I'll make a video of it and see if I'm right or wrong. And I don't know, maybe I should have made that a discussion topic. Anyway, thermosets do not achieve liquid-like state. So as the temperature rises, the cross-links prevent chain movement, which, if you're listening to my diatribe, my side debate, the fact that they heavily cross-link to high-density polyethylene maybe does thermosetize it to the point where you can't soften it. Okay, so these crosslinks are heavy crosslinks. They're hard crosslinks. They're not weak crosslinks like hydrogen bonding or chain entanglement. They're probably covalent bonds. Okay, so that's a strong crosslink preventing chain movement. Decomposition. So thermosets don't melt. Okay, they decompose, and there's two flavors of decomposition for a thermoset. A chain scission can also affect thermoplastics, and water affects certain polymers. So polylactic acid, PLA, one of my faves, it's hygroscopic, and if a material is hygroscopic, that means it can undergo changes in the presence of water. And so what happens is you start chopping up the chains, just like the name means, and so you have these smaller polymer chains floating around, so your mechanical properties take a dive, basically. The other thing that can happen for decomposition of a thermoset is depolymerization, where you actually break the bonds between your individual MERS, and you just have a blob of MERS laying around, no chains, so they're depolymerized. It's just burnt, nasty goo. So thermosets decompose. This is, I don't know if I want to read this, but you can pause it. This is actually a pretty powerful slide because it has a lot of information. And so creep is a really bad part. It's a huge failure mechanism for polymer parts, especially under constant load. And we'll talk about polymer failure analysis before this semester is over. But creep is a huge problem. And what happens is thermosets don't exhibit creep or as much creep. This one says very little creep. But however, thermosets are generally more brittle than thermoplastics. And so if you're using them by themselves, it's bad, right? But composites like, the so-called graphite epoxy composites, the matrix a lot of times is a thermoset epoxy. And but you're overcoming some of the problems by putting in the carbon fibers, right? That's why you make a composite, to either achieve a new physical property or to overcome some problem with the matrix. And some of you may be taking composites or have taken composites, and you're well aware of that. Anyway, I'll let you pause it or something if you're interested in this material. Epoxies, so like JB Weld, the raw materials, they can go bad and stuff like that. Fusion welding is generally heat, so sometimes one flavor is using hot air. I'm actually reading the slide to you, and I said I wouldn't, but now I started getting interested in the content. So hopefully you get interested in the content. So fusion welding, a lot of times there's a hot air. It's like a very fancy hair dryer. And you could also solvent weld, and so a lot of glues, like model glue, is actually a solvent welding glue, so you can dissolve it, and then it re-solidifies, but it melts together, that kind of thing. So take a look. This is a nice slide comparing thermosets and thermoplastics. Pause it, read it, may come up on a quiz. You never know. Now we're segueing into rheology. We've talked a little bit about rheology. We've talked about some terms already that we see, and I even mentioned viscoelasticity already as well. So we look at elasticity, viscosity, and viscoelasticity. It's like elasticity when we talk about rheology, excuse me. So rheology, it's the study of material flow and deformation. And rheo, R-H-E-O, not one of the capitals of Brazil, the other being Brasilia, useless trivia. Ology, the Greek word for science or study. So rheo is the Greek for flow. Ology is Greek for science or the study of. And so metrology is the science of measuring. Rheology is the science of material flow or the studying. All right, so we have our definition of rheology. Here, this is a really high level way to think about this stuff in terms of shear disk deformation. So shear stress, tau, is force over area, And so shear stress we're still getting the same units that we would have stress when it's denoted by sigma. Okay, shear strain, gamma U over H, and so it's this deformation divided by this deformation. I know there's a lot more to it than this, but we're talking at a really, really high level. Shear strain rate also given by gamma, but we have the dot, that's why it's a rate, is the rate of deformation of U over H, basically. So this is just a high level. So shear stress, shear strain, strain rate. Shear is involved in viscosity measurements because it's extremely hard, almost downright impossible to measure viscosity without shear. And that is kind of plays into the discussion topic for this week as well. So some equations for elasticity and viscosity. So we have Hooke's law in terms of shear. The other flavor of Hooke's law is sigma is equal to E epsilon. When we're talking about like stress strain curves, here we're talking about shear. And so shear stress, tau, is given by the equation tau equals G, which is the shear modulus, gamma, which we said was the shear strain. And for an ideal viscous liquid now, this is a Newtonian viscous liquid, tau, which is the shear strain, is equal to eta. I believe this is eta. It's a dynamic or absolute shear viscosity times the shear strain rate. And this is given in the units of Poise, excuse me. So dynamic or absolute shear viscosity is given in units of Poise. And so a Poise is 1 dyne second per centimeter squared. And a Newtonian fluid can be described in terms of temperature and pressure. Okay, so that's a kind of a characteristic of a Newtonian fluid. If we look at a non-Newtonian fluid, and I kind of throw this another definition of a Newtonian fluid, where a Newtonian fluid exhibits a constant viscosity independent of stress. If I look at a non-Newtonian fluid, and we can kind of compare the two, okay, a non-Newtonian fluid, the viscosity is going to change with a change in shear rate, basically. And for a Newtonian fluid, it should remain pretty much constant. That's the definition of a Newtonian fluid. For all intents and purposes, I tend to use non-Newtonian fluid and viscoelastic material interchangeably. It's important to note that not all non-Newtonian fluids exhibit viscoelastic response. In the case of polymers, though, pretty much most polymers exhibit non-Newtonian characteristics as well as a viscoelastic response. And so let's take a look at some examples of that. All right, so examples of viscoelastic material and our non-Newtonian type of fluid, if you will, is like silly putty. And if you stretch it slowly, it stretches, 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 stretches. If you come and stretch it fast, it breaks, okay? Before you get to the same elongation that you saw before. And you see this behavior also in polymer tensile tests as well. And we'll talk a little bit more about the mechanical properties of polymers. But it's important to keep this in mind that the polymers really don't have a true modulus, even though it gets reported as an elastic modulus. And that's because of viscoelastic flow. And ASTM standards for polymeric specimens have different specifications for strain rates depending on which you're pulling. Another example of a viscoelastic material, or non-Newtonian fluid, if you will, is the putty we made for the slime we made for the making slime video. And one kind of characteristic is it tends to take the shape of the container it was in. And you saw it, last time you saw it, it was rolled up in a ball and bouncing. And so we stored it in a plastic bag so it would dry out so we can play with it later. And it's taken the form of the bag, the plastic bag, the container it's poured in. So that's another characteristic of a viscoelastic material. And we're going to take a look at an experiment that we did
with my junior TA again here in a little bit.
All right, so we have an experiment again featuring my junior TA Isabella, and we've done the made oobleck, and he makes cornstarch and water to achieve what's classically known as a non-Newtonian fluid, but it also exhibits viscoelastic response. And she's going to show you right now. Boom, she's hitting it, she's getting used to the feel, but when she pushes slow, her hand starts sinking into the substance. And so now she's hitting it fast and hard. Boom. So there's a difference in strain rate, if you will, between that and now she's going to go slower, and her hand just sinks into it. And the fluid's kind of interesting, and she kind of shows some viscoelastic response there, kind of silly putty like. And she kind of changed the strain rate, trying to get her hand out of it. She's going to try again, I think with her other hand, because the other one was dirty. Maybe not the other hand. Boom. And she's hitting it again. Kind of changed the rate a little bit. You see a difference in the behavior of the material. And it's really interesting stuff when you touch it. And then she's letting her hand sink into it again. And so another experiment using commonly found household items. Literally, that was just cornstarch and water. And some of you have probably done this before, but it's always kind of cool to see this kind of material behavior as well. And polymers typically, or some polymers anyway, go through this type of response. All right, so we saw an example of viscoelastic-y stuff, and several examples in the experiment actually. So now let's talk about the units of Poise and the accepted abbreviations for Poise or CP or CPS. That would be centipoise, excuse me, CP or CPS. One Poise is 0.1 Pascal second. 1 Pascal second is 1 Newton times second over meter squared equals 1,000 centipoise. Okay, and I think the units work out. All right, 1 Pascal is 1 Newton per meter squared. So I'm kind of a stickler for units, which is why I go into this kind of stuff. To make it more practical, I have a table on the next slide which kind of shows the differences in centipoise or viscosity in terms of centipoise for various materials. So viscosity is a common stuff, and so this is the viscosity of centipoise. This table is using the CPS. I like CP because to me CPS means counts per second. I borrowed it from this website here. It's a viscosity table. And so water going all the way to peanut butter. And peanut butter is 250,000 centipoise, and that can be pretty viscous. And water, 1 centipoise, I think that's because viscosity, or the unit of measurement of viscosity, was actually originally based on water. Kind of like a cubic centimeter of water is a milliliter of water, that kind of crossover. Anyway, I hope that's not incorrect. But anyway, we can see the viscosity of motor oil increases for the grade. We start getting into Karo syrup, which is basically corn syrup, honey, chocolate. I'm assuming this is molten chocolate. Ketchup, mustard. Ketchup is also a non-Newtonian viscoelastic material. Sour cream and peanut butter. So in the 3D printing processes, we see viscosities ranging from I want to say about the ketchup mustard range all the way to the peanut butter range. When we're doing thermoplastic extrusion, I put it on this next slide. We can be kind of in this similar range, but they can go all the way up to 1,000,000 CPS. In my lab, I don't think I do anything much higher than peanut butter in terms of viscosity. Kinematic viscosity, mu is the Stoke, and that's centimeters squared per second. The Stoke, or kinematic viscosity, equals, and I already forgot my own word, the shear viscosity excuse me, that was bad of me. The shear viscosity over density and the kinematic viscosity can also be given in terms of meters squared per second. How viscosity is measured. One is a capillary viscometer and asphalt. So we have the Center for Highway Materials Research. They do a lot of asphalt testing. And I've not talked to them directly, but maybe this is one of the ways they measure the viscosity. Another way is an actual rotational viscometer stand. One thing I want to kind of point out here is this doesn't really use shear, okay? But they're using something that, so when I think of shear, I think of like an egg beater or something, right? You know, putting a paddle in something and stirring it, and you know, you can look at James Bond. I can't remember, does he like his drink shaken and not stirred? There's a difference in the mixing when you put shear to the material. And to me, this doesn't look like it's shear, but I actually know how this works. It works on the Huygens Poisoli, I'm going to pronounce it wrong, method, and we'll see that method again. But these guys are individuals measure viscosity through a non-shear mechanism. I'll give you a little bit of foreshadowing. I'm giving away the punchline, but that's okay. The material travels from one orifice to another diameter. I shouldn't say orifice, I guess pipe, for lack of a better term. That shrinking of diameter is said to put shear on the material, and that's why you can measure viscosity. And I'm kind of giving away some stuff for the discussion board topic as well. This looks more like a rheometer. Our viscometer, rheometer, viscometers kind of do same things. There's rheometers, and some people like rheometers, but a lot of times rheometers give you similar information to a DMA, so I still like the DMA. Anyway, this is a viscometer. It's again like an egg beater kind of thing, and so you measure the resistance to the egg beater, to the shaft turning the little beater unit. And that's how you figure out your viscometry, and an ASTM standard for that. Melt flow indexer. Okay, so we saw the MFI video. Here is a diagram of the MFI, and you can kind of see that there's differences in diameters here. And so I'm not going to say anything else because you have a discussion board, and you also see a video of how this test is actually done. But the discussion board topic is MFI, a measure of viscosity. And I can give you a hint, there's conversion charts. Okay, so hopefully that helps with the discussion board topic. And I was trying to find Brainy Smurf, but I think Brainy Smurf wears glasses. This is just a guy on the side of the street, Smurf. But he's pondering the question as well, so he's all right with me. Here's the equation that you can use now, and I know this gentleman Nam So, aka Peter Kim's at our school, but when I read this paper, I thought it was actually pretty cool, and I invite you to read it. I'll post it for you to read, because really what they have done is they're using mu to get your dynamic fluid viscosity and centipoise. And they used the 3D printer as a viscometer, and I read this and I thought it was pretty cool, and I thought it was pretty neat. And this is the Huygens-Poisoli equation. It's a variant of the Huygens-Poisoli equation, and it's the basis of what the civil engineers would use to measure the viscosity of asphalt, basically. And the Huygens-Poisoli equation, you have a material flowing through, so they figured out the amount of material flowing through the liquefier in their 3D printer. They could figure out the same way with this glass tube that the civil engineers would do. And you have the different variants. So you have the length of the tube, you're solving for mu, and then you know some pressure difference, right? Because on MFI, it's more apparent because you're actually putting a weight on top of it. So you could actually figure out the pressure, force over area, right? And you could figure out the force over area for orifice A and orifice B because there's a change, or maybe you can measure it here. I'll let that be up to you for the discussion board anyway. Anyway, very good way. The kind of the classical depiction of the Huygens-Poiseuille equations. This is a little bit more classical. However, they just made a variant of the same equation, I believe, right? So very good work. So go miners on that one. So we've talked a little bit more about polymer classification, kind of tied that into rheology. We've talked about methods to calculate glass transition temperature, apparati to calculate the viscosity. Kind of pondered a little bit more, can you use an MFI to determine the viscosity of a polymer? And I'm almost giving it away. I mean, you saw a gentleman, one of our own UTEP minor professors, using a 3D printer actually as a way to measure the viscosity of the polymer. And so hopefully that helps. And hopefully you've enjoyed seeing the experiments. And if you have any questions, feel free to email me. And as always, thank you so much for your time.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.